So in this lesson, we're going to take a look at the trigonometric form of a complex number. And before we get started on that, though, we're going to talk briefly about the complex plane. So starting with the complex number z equals a plus bi, the complex plane consists of a real axis and an imaginary axis. So no longer x's and y's, but real and imaginary. And the point AB, where A is the real part and B is the imaginary part, could be plotted in a similar way, where it's a distance horizontally of A and a distance vertically of B. And so I'll go ahead and construct now a right angle, and we'll call this R, we'll call this theta. And by observation, we can see that cosine of theta would be A over R. Sine of theta would equal b over r. In other words, a equals r cosine theta and b equals r sine theta. Now, if I take the a value and the b value and I plug them in to the original complex number, we would get z equals r cosine theta plus r sine theta times I. And simplifying it by factoring out the r and putting the I in probably a more appropriate place, we can see that r cosine theta plus I sine theta is another representation of the original complex number. And so this is considered the trigonometric form of a complex number. So in the first example here, we're given a complex number in its a plus bi form, and they want us to write it in its trigonometric form. So we know that we're looking for r cosine theta plus I sine theta. And we also know that all of this came from a triangle that we've seen many, many times, where that's a theta, that's an r. We talked about a's and b's. We talked about a real axis, and we talked about an imaginary axis. So if I'm needing to find r, it looks like by the triangle, the Pythagorean Theorem is going to be the easiest way to do that. So for r, we're going to get the square root of our a, negative 2 squared, plus our b, negative 2 root 3 squared, which would be a 4 plus 4 times 3 is 12, so it looks like the square root of 16 would be 4. And then for our theta that we're missing, just like we've done again many times, we would probably go with tangent of theta now equals the b over a. So the b would be negative 2 root 3 over the a, which is negative 2. So we get a positive root 3 out of this. And so tangent is positive in quadrants 1 and 3. And to see which one that we're dealing with, again, I'll come back up here to the original, knowing that I move in the negative direction for the a and the negative in the direction for the b. You can see that once again we'd be down here in quadrant 3. And so for tangent, this is a special triangle, and so this would be a negative square root of 3, a negative 1, and a 2, which means our reference angle would be a pi over 3. So pi plus pi over 3 gives us 4 pi over 3, and so there's our theta value. So our final answer then, our complex number that we started with, z, would equal 4 cosine 4 pi over 3 plus I sine 4 pi over 3. So again, just a different way of writing the complex number. So in this problem now, they start us off in the trigonometric form, and they want us to write it in the a plus bi form, which means that we need to find a and we need to find b. Now, just a moment ago, some of the connections we made showed that a equaled r cosine theta and b equal r sine of theta. So you can see from the original problem, our r value is given as 1/2. Theta was given as 5 pi over 6. So I'm really just going to need to now take these two values, plug them in here, and then we'll find out what a and b are. So a is going to be 1/2 cosine 5 pi over 6. B would be 1/2 sine of 5 pi over 6. 5 pi over 6 would be up here in quadrant 2, so giving us a reference angle of pi over 6. So that would be a 1, a 2, a negative root 3. So 1/2 and then cosine of 5 pi over 6 would be negative root 3 over 2. And sine of 5 pi over 6 would be a 1/2. So simplifying, we find out that z would equal negative root 3 over 4 plus 1/4 I. So there's the a plus bi form for the original complex number that was given in its trigonometric form to start.